So what do we mean by linear independence in linear algebra? So what we mean essentially is that a vector is independent of another set of vectors, which could be one vector or several vectors, if it cannot be expressed as a linear combination of those other vectors, which is to say a vector is independent if it's not in the span of the other vectors. And this is a mutual thing. So you don't, if you have a set of vectors and you want to know if the set is independent, what you need is for all of the vectors, if we take it out and we compare it to the other vectors in the set, that it's all of the combinations of these are independent of each other. So any vector that's dependent on any other vector in the set that is a linear combination of any single or multiple vector in the set would be dependent, and that would make the whole set dependent. All right, so there are some ways that we can look at a set of vectors and sometimes by inspection identify whether or not there's going to be whether the set is going to be independent or not. Now, some of these students generally have no problems with, and there are some of these properties that students struggle with because they over apply it. So they apply it in situations where it doesn't actually work. So let's start with the one that people don't generally have problems with. So if you have a set of vectors with more vectors than there are vector components, i.e. the dimensions, then the set must be dependent. So let's say I have a set of vectors do 4 vectors, and let's say I have 2, 3, 0. That was not a 3. And 4, 1, -1, and 9, 11, 12, and 0, 0, 1. It does not matter what the components are. They don't have to be pretty scalar multiples, but I have only 3 dimensions, and therefore I only need 3 vectors to span all of our 3. The fact that I have a 4th vector guarantees that at least one of the vectors is going to be linearly dependent upon the other 3. Now, you can have, for instance, if you could end up with a situation where you only span 2 dimensions instead of 3 dimensions. But what you're looking at is the entire set. And for right now, we have more vectors than we could possibly have that could be independent, and therefore this is dependent. So a set like this must be dependent because there's too many vectors. If your set of vectors contains the 0 vector, the set is dependent because there is more than one linear combination. And it doesn't matter how many vectors there are. If any of them is 0, then the set is dependent because I can multiply 0 by anything and add it to another vector, and I can treat it as a linear combination of the 0. So, and again, 0, I can multiply both of these by 0 to get 0. It is a linear combination of the other vectors. So again, anytime you see the 0 vector in the set is dependent. Now, the one that students tend to struggle with is that if you have a set of 2 vectors and they are not scalar multiples of each other, then they are independent. And again, the size doesn't matter. So 5, 1, -1, 0, and 10, 4, -2, 0. If they are scalar multiples, then they are dependent. If I change one of the components, and now they're not scalar multiples, these are independent. Again, but this only applies, and again, I cannot stress this enough, this only applies when you have only 2 vectors. The minute that you go up to 3 vectors, you can't use this rule anymore. Now, it is true that if you have a set of 3 vectors and you can identify that one of them is a scalar multiple of the other, that will make them dependent, because that is one way of getting dependency. But if you don't see scalar multiples, that is not a guarantee that the set of vectors are independent. So let's look at an example. So let's say I have 1, 2, 3, and I've got 2, -1, 1, and then I add the 2 vectors together to get 3, 1, 4. Now, this first vector and this third vector are not scalar multiples of each other, and the second vector and the third vector are not scalar multiples of each other, but this third vector is the sum of the first and the second vectors. So these are dependent, even though there's none of these vectors are scalar multiples. But the third vector is a linear combination of the first 2 vectors. And those linear combinations, sometimes if you stare at a set like this long enough, you'll be able to see, oh, I see how they got that third vector. It's by doing this and this. Sometimes you can spot that. And if you can spot that, then you can say, oh, they're dependent because this vector, I can take this vector and multiply it by this, and I can take this vector and multiply that, and if I add them together, I get this one. If you can do that by inspection, then you have identified the dependency relationship, and so then you can say they're dependent. But if you don't find that, and you don't find that they're scalars, you cannot claim that they are independent, because you might just have missed the linear combination that you need in order to get to that third vector. So in this scenario, you can't, again, sometimes you can spot it by inspection, but if you can't spot it by inspection, then you need to row reduce a matrix with these vectors and count the pivots. And if we were to, in fact, do that for this exact set of vectors, I row reduce this, then what I'm going to get is 1, 0, 1, 0, 1, 1, 0, 0, 0. So I have no pivots. And in this column where I don't have a pivot, what you'll get are, in fact, the multiples of the other two vectors that you'll need in order to get the final vector as a linear combination of the others. So I added one copy of this one to one copy of this one to get this one. And in fact, you can see that the 1, 1 is telling me exactly the same thing. One copy of the first vector plus one copy of the second vector produces this third vector, and there's no deviation from that. So there's no pivot here. So again, sometimes you can spot dependency, but you can never be completely sure that it's independent unless you do the row reducing and count the number of pivots. Now, once we have vectors that are linearly independent, then we can go on and we can do a bunch of other things with them. Linear independence is often a requirement for various theorems. When we do regression, for example, the whole normal equation is going to require columns of our matrices to be independent. We need them for establishing a basis for a space and so forth. So this idea of independence is going to come back up again. But again, typically when you have three or more vectors, if there's not some obvious dependency, then you should row reduce because you just normally cannot declare there's no scalar multiples, therefore it's independent. That simply doesn't work. It only works when there are only two vectors.